Hi everyone. Now we want to move on to the next topic. We want to talk about dynamic set. And you may say, what is a dynamic set? Is that a data structure? If you have taken the data structure course, then you may know this word. That's called abstract data structure. Okay, so dynamic set is not one specific data structure we are talking about. Well, say if you say a linked list, and then that is a data structure. But for dynamic set, we call that a abstract data structure, and we can implement this functionality that can facilitate all the behaviors of a dynamic set using different implementations or different data structures. Okay, so let's first take a look on what we want to have using a dynamic set. So for a dynamic set, we are using a key, and then behind the key we have the satellite data associated to this key. Okay, and then all the data will be organized like this. So using a key, and this key, behind this key we have a set of satellite data, and then another key, and then another set of the satellite data. Okay, and then for the dynamic set, and we want to support a query like we want to search using a key, we want to get the minimum of the key, we can get the maximum of the key, and then if we have one node or one value, and then we want to get the successor and the predecessor, which is if we want to sort out the keys, and then you have the key X, and then what is the key before X, what is the key after X. Okay, and then we can also do the insert and then delete. Okay, so you may ask, why do we really need this dynamic set? Okay, let me give you an example. And say if we are managing the registration system for our university, and then we don't have a lot of students, but we have tens of thousands guaranteed. Okay, and then for each student, what can be the key? The key could be the social security number, or it could be your campus ID. For both the social security number or the campus ID, and for each of the student you have a unique that key. Okay, so anyhow, if we have the key, and the next question is, before we open the registration for a specific student, we want to remind this student you owe X amount of the tuition before you can start your next semester. Okay, we just want to show this information. And then how do you get that information? Okay, and you may say it has to be somewhere in the database. You are correct, it is in the database, but how do you want to query the database and get that? Okay, and assume the database runs on a sequential search. And is that cool? Probably not, right? Because you have a student ID, and then you have to query the entire database and visit all the possible records one by one, and before you find this student's record, and then you show this information saying, okay, you owe 1,000 before you can proceed to next semester. This will take some time, and our university is not too big, but we can definitely have even bigger universities. So a quick query is the key for the dynamic set. Okay, we want to have a implementation of the dynamic set that facilitates fast queries. Okay, and then how do we do that? And then we have the binary search tree. Binary search tree is a data structure. However, the dynamic set we just talked about, that is a abstract data structure. We can implement dynamic sets using different ways, and one of the way is to use binary search trees. Okay, so for the binary search tree, and the short name is the BST, and sometimes we will use the BST in our class. Okay, and then for each node of the BST, and remember we want to have the key, right? And other than the key, and then we may have multiple pieces of the satellite data. And one piece of the satellite data could be, say, how much tuition does this student owe? And another satellite data could be where we can find where we can find the academic probation information, saying whether this student is in academic probation or not. Okay, and then other than the key and the set of data, and then we also have two cursors, one cursor down to the left child and another cursor down to the right child. And then, well, we also want to have another P, which is the pointer or the cursor pointing to the parent node. Okay, and then for the left child, right child, and the parent, and if you don't have such a node associated, and then it can be a null. Okay, and then for the BST property, we want to enforce one property to the BST and to the root of the BST and all the possible subtrees of the BST. And the rule is for the key on the left side, it's going to be smaller or equal to the key of the parent, and then the key of the parent is going to be smaller or equal to the key to the right child. Okay, and then for example, if we have such a BST, and then well, yeah, we are using the letters instead of the numbers, but you get the point. So f is greater than b. Okay, so well, b is a left child of f. That is okay because b is smaller than f. And h is a right child of f. So and h is indeed a larger value than f. And then we want to enforce this rule to all the possible parts or the subtrees of the BST, even for this part. So for the h, it doesn't have a left child, so that's okay. But if you have this h has a left child, and then this left child is going to be smaller, it's going to be smaller than h. And then for the k, that is the right child of h, and then indeed k is higher than h. Okay, and then the next question we want to say is, how do we visit all the values, or how do we do the search? And why do we want to do the search? Well, remember, one of the important things we want to implement with a dynamic set is we want to facilitate quick searches. And if you want to check a student information, we don't want to do a sequential search. We want to do a faster search if possible. So how do we do the search? And before talking about that, we have to understand an important concept, which is tree walk or tree traversal. Okay, for the tree walk or the tree traversal, this is the approach that we can do to visit all the nodes of the tree one by one. So how do we do that? Well, in our textbook, the first way we see is, well, we want to do a tree walk, and then we want to do a recursive tree walk of the left subtree, and then we visit the root, and then we will do another recursive tree walk on the right subtree. Okay, so this is one of the common way to do a tree walk or the tree traversal. We want to do a recursive tree walk on the left subtree, then the middle, the root, and then we go to the right subtree and then do another recursive tree walk. Okay, and if we are doing this with a binary search tree, and one of the interesting you will find is, well, this tree walk or tree traversal is guaranteed to touch or to print all the tree nodes in a sorted way, in a increasing order. Okay, and this is called Inorder tree walk. So we are visiting the root in the middle. Okay, this is called Inorder tree walk. And similarly, if you want to do a pre-order tree walk, and then you are putting the print, this line, at the very beginning. Or if you want to do a post-order tree walk, and then you want to put this print at the very end. Okay, so there are three different ways in order, which is to put this line visiting the root in the middle, or the pre-order, you want to use this line at the very beginning, which is here, or you can do a post-order tree walk, which is to use this line at the very end after you have visited both the left subtree and the right subtree. Okay, those are three different ways of doing the tree walks. Okay, so let's use this one as an example, and then let's do a in-order tree walk. So we want to start from the root, right? And then how do we do that? We want to tree walk the left subtree. So we want to tree walk this part of the subtree, and then we will visit the B, which is the root of the subtree. And then again, this will tell me to tree walk the left subtree, which is A. Okay, and for the A, well, you will check, okay, for the left child, that is a null, saying there's no left child. And then again, there's no right child. So, oops, sorry. So we will first visit the left side of the A, and then we will say, okay, it is a null. And then we will do a print of the X. So we will print A. And then we will do a tree walk of the right side. So what's on the right side of A? Nothing, right? So this means, well, from the B, the standpoint of the B, the left subtree, which is A, has already been successfully and fully touched. And then we want to go here, we want to print the value of the B, and then we will start a tree walk of the right side of the B, which is D. So at the D, we will find that there's nothing on the left side, we print D, and then we find there's nothing on the right side. So at this point, we have already successfully done the tree walk of the ABD subtree. And then we will go to the F. We will print the F, and then we will go to the right subtree of the F, which is H and K. For the H part, we will first try to touch the left subtree. The left subtree is empty, so there's nothing there. Then we will do a in-order, which is this line. So we will print H, and then we will go to the right subtree of H, and then we will print the K, right? Okay, well, this is how we do a in-order tree walk. The sequence will be A, B, D, F, H, and K. Okay, so the next question I want to talk about is how long will a tree walk take? Well, you may have this feeling. The feeling is we are touching each of the node once. We are only printing the value of such a node once, right? So if we have n nodes in the tree, what does this mean? This means, well, a tree walk will take a theta n time, right? Precisely, we are visiting all the nodes and printing the value once. So that is a theta n algorithm. So my next question is, how do we prove that the in-order tree walk is guaranteed to print all the values in an increasing order? Or how do we prove that when we are doing a in-order tree walk, it's guaranteed to print all the elements in a sorted order? So how do we do that? And say, if we are visiting the B, okay, and then when we visit the B, and then, well, there are two possible cases. If there is no left child of the B, and then that's one condition. And then if B has a left child, and then remember we talk about the property of the binary search tree. This means if B has a left child, this left child is guaranteed to be smaller or equal to B, right? So when we are doing the in-order tree walk, we will touch the left subtree before coming to B. So this will guarantee that all the values smaller than B will be touched and printed before we print the value on the B, right? Okay, and another scenario will be like this. So if we are touching the H, well, on the side of the H, we don't really have a left child. So this means when we are touching this subtree, there's really no value smaller than H. So in this case, we are going to print the H first and then go to the right subtree of the H if there is any. Why? Because there's no other value smaller than h anymore. So we have to print the h, and then we move on to the right side if there is a right subtree, right? So in either way, either in the scenario of b or in the scenario of h, well, we are doing the right thing. This will guarantee that when we are doing the in-order tree traversal, we are printing all the elements or all the key values from the lowest to the highest. Okay, so well, this is for the tree walk or the tree traversal. We talk about 3 different ways of doing the tree walk. We have the in-order, pre-order, and post-order. And for the in-order, that's one of the interesting one because we are making use of the property of the binary search tree, and we are printing all the keys from the low to high. Okay, so let me stop here, and the next video we are going to continue our discussion about the binary search trees.